So this lecture is covering section 2.4 in our book on polynomial maps. So the objects that we are going to study in this section are maps from two different polynomial ring spaces. Maps between two different polynomial ring spaces. So in particular, if we have a map phi that goes from one ring, say K bracket y1 through ym, and maps into the ring K bracket x1 through xn, so we're keeping the field the same. We've seen that we can view these rings as both rings or K vector spaces, right? So what we want are maps that preserve both properties. So these are called K algebra homomorphisms, and they are both ring homomorphisms and K linear transformations. So first we want to observe that if we have such a map phi that is both a ring homomorphism and a K-linear transformation, is completely and uniquely determined by where it sends each of the variables y1 through ym. So each variable y1 through ym can itself be viewed as a polynomial sitting in this space, so it has to go somewhere via phi. It gets mapped to a polynomial in this polynomial ring. So let's say we call phi of y1 f1, phi of y2 f2, and phi of ym fm, for example. Then knowing what these fi are completely determines what happens with the map. That's because phi is both a ring homomorphism and a K-linear transformation. So a polynomial is constructed from these variables y1 through ym by products and coefficients. So if the map is maintaining those structures, it will maintain the structure of the polynomial, and knowing where each individual variable goes is enough to determine it. Okay, so we are going to call this ring R sub y for shorthand, and this ring R sub x. Okay. So next we want to look at the kernel and the image of this map. So we can define the kernel, of course, to be those polynomials in Ry that map to 0. This is an ideal of Ry. And the image being those polynomials that are in Rx and come from something in Ry. Is a K subalgebra of Rx. Meaning it has the subring and subspace property. Okay, so using the first isomorphism theorem for rings, of course, the image of phi in Rx is actually isomorphic as a K-algebra isomorphism to Ry mod the kernel. A couple more observations. One, if we take some h in Ry, then we know that h looks like some sum with coefficients, say c sub alpha over an indexing set alpha, where our variables are all y variables. And we have only finitely many of the C alphas are non-zero. So the reason I want to write it this way is so we can observe that if we look at what happens when we send H through our phi map, what happens is, because phi is a homomorphism and a transformation, it breaks up over the sum, the constants come out, and the powers come out as well. So we get that this is C alpha phi of y1 to the alpha 1, phi of ym to the alpha m. And since we established before that the yi's are going to the polynomials fi's in our notation, this is exactly f1 to the alpha 1 through fm to the alpha m, which is equal to h, where the fi's are now plugged in for the variables. And this is our x. Okay. So, in general, we see that phi of h is the same as h evaluated at where the y's get sent. We also see that h is in the kernel if and only if h evaluated at the places where the y's get sent is 0. So now we can discuss what our main goals are for this section. So we have 3 goals. Our first goal is to compute the kernel of such a map phi by computing the Grobner basis for it. Well, I guess maybe a better way of stating our first goal is just to determine the kernel. Our second goal is to determine ideal membership in the image. And our third goal is to determine when the image is when the map is onto. Okay, so those are our 3 goals. So our first goal is answered by the following theorem. So, given a map K-algebra homomorphism phi from Ry to Rx with phi of yi equal fi for all I, we let A be the ideal of Rxy, so we'll define Rxy to be the polynomial ring with all the variables. So we'll define the ideal A to be y1 minus f1, so generated by y1 minus f1 to ym minus fm. The y's obviously are in Ry, the f's are in Rx, so together this is in Rxy. The theorem says that then the kernel of phi is equal to the intersection of A and Ry. So that theorem answers question 1. In order to prove this theorem, we first need a technical lemma. So given elements of a ring A1 through AN and B1 through BN, so this is going to be a commutative ring, then the element that's the difference of the product of all the A's and the product of all the B's is in the ideal generated by the individual differences of AI and BI. So the proof of this technical lemma is not too hard. We use induction, and the n equals 1 case is easy because then we just have A1 minus B1, which is clearly in this ideal. So we assume up to n minus 1 that this is the case. And then we observe for n that this difference can be written as A1 times the difference of A2 through AN minus B2 through BN. So that gives us 1/2 of what we want here, but now we have this extra A1 times B2 through BN term. So we want to add that back in. And we get that by adding the product of B2 through BN and A1 minus B1. So now we've got our negative B1 through Bn here, and then the wrong terms are canceling. Well, this part is clearly in the ideal because we have an A1 minus B1 as a product there. This part by induction we can assume is in the ideal just without this first generator. So together they're clearly in the ideal we want. Okay. So now we can prove theorem 1. We'll utilize that lemma. trying to show an inequality between two sets, so we just need to show each containment. First, we'll show that A intersect Ry is in the kernel. So let's take an element, call it G, and we'll let that be an A intersect Ry. So G is a polynomial with only variables in y that's also in this ideal. So we know then by definition of the generation that G is equal to some combination, so of the yi's minus the fi's. So let's call the multiples hi, where the hi's are in the full ring Rxy, so variables in both x and y. Okay. Then if we plug in, so G has y variables. If we plug in fi for each yi, we'll see that these terms all cancel, and so we'll get 0. But as we saw before, that's what phi of G is G evaluated at the places that y gets sent, which is the fi's. So that means that G is in the kernel of phi. So that direction is proved. Now we want to go the other way and say that anything in the kernel has to actually be in the intersection of these ideals. So let's let G be in the kernel. Then what we know is that phi of G, or G of f1 through fm, is 0. We could also write out what G looks like, and this is how we'll use our lemma. So we know that we can write G, as we did before, as some field element, C alpha, times the variables y1 through ym to some powers, alpha 1 through alpha m. And I won't write the details about the alphas a second time. And we know by our hypothesis that G is in the kernel, so we know phi of G, which is G of f1 through fm, is equal to 0. So that means if we plug in f1 through fm, we get 0. So we could rewrite this as, cleverly, we could write G as G minus 0, but we could write 0 as G evaluated at the f1, fm. So what essentially we have here then is G at the y1 through ym variables minus G at f1 through fm is so we have G rewritten as a difference of G at the y variables minus G at the f variables, at the f polynomials. And then using this way we're writing out G, we can see that that's actually a sum with coefficients C alpha of the difference of the product of the y variables and the powers. Let me write this a little bit narrower. So the difference of the powers, the product of these y's to powers minus the f's to the powers. And now it looks like we can use our technical lemma. So our technical lemma says that this difference is actually in the ideal generated by the individual differences, which was A. So this is in A. by the technical lemma. So that means that G is in both A and, by definition, since it's in the kernel, it's in Ry. So it's in the intersection of A and Ry, which is what we wanted. Okay. So to conclude the solution of our first goal, I would just like to mention practically how one would attack this problem using our Grubner bases. So one, we compute a Grubner basis for the ideal A. Which we recall was generated by the differences of the y variables and where the y variables get sent under our map phi. We do that with respect to an elimination order where the x variables are greater than the y variables. Then, the polynomials in that Grubner basis that are only in Ry form a Grubner basis for the intersection, which is the kernel. So let's call it Grubner basis G. Then the polynomials in G intersect Ry form a Grubner basis for A intersect Ry, which we now seen by our theorem as the kernel that we are interested in. So that's using our elimination theory from last class. Okay. So that is goal 1. Now we move on to goal 2, which was to determine, given a polynomial, whether it's in the image or not. This is solved by the next theorem, theorem 2. So again, let phi be our map from Ry to Rx. And let phi of yi be fi. And define A to be our ideal y1 minus f1 through ym minus fm. An ideal of Rxy. And let G be the unique reduced Grubner basis for A with respect to an elimination order where the x variables are larger than the y variables. Then a given polynomial f in Rx is in the image of our map phi. Let me write it slightly differently. So for f in Rx, we can say f is in the image of phi if and only if there exists an h in Ry such that f reduces to h via g. In such a case, f is phi of h, which we've seen is just h of f1 through fm. Okay. So that's theorem 2. To prove it, we need to prove both directions. So let's start with the reverse direction. That's a little bit faster. So we want to assume that we have, we want to assume that f reduces down to a polynomial just with y variables using the Grubner basis and show that it has to have a preimage. So suppose f reduces via g to h with h in Ry. We know that f minus h is in the ideal A, for which g is a Grubner basis. So that means we can write it in terms of the generators of A. So in particular, we could write f minus h as a sum yi minus fi times the multiples that are in, let's call them gi, that are in our xy in both variables. Now plugging in fi's for the yi variables, of course, gives us 0 on the right side. So here, f is in terms of the x variables and h is in terms of the y variables. So if we plug in f for the y variables, what we get is that f of x1 through xn is equal to h of f1 through fm, which we've seen is just phi of h, and that indicates that f is in the image. Alright, so that's one direction. To go the other direction, we need to start with some f in the image and show that it has this property that it reduces down to a polynomial with only y variables. So let's start by assuming f is in the image of phi. So then we know that f is equal to phi of g for some g in Ry, and we know that phi of g is the same as g evaluated at f1 through fm. So now what we want to consider the difference of f minus